Okay, so let's talk about domains for a second. And it's really sort of hard to talk about domains without talking about ranges, so let's talk about both of them. Okay? So, what's the domain and what's the range? Are you thinking for these things? Yeah, I mean, kind of. You'd really kind of think about x's here. And you could kind of think about y's here. What else could you think? What are the x's? Yeah, the x's are the inputs, right? So really maybe the more precise thing is to think about the domain as being the set of all the inputs that work. If I want to think about the range, what's the range? Yeah, it's all the outputs. Okay, so maybe a really easy example. Something like f of x is x squared, right? Okay, so what kinds of numbers can I fit into the function x squared? Yeah, basically whatever, right? You see that? I can take a number and multiply it by itself. I know what I should get out of that. That means that the rule's not broken there. That means those are valid inputs, right? So my domain on this guy is the funny R. This happens pretty often, especially at this stage of the game because we play with basically nice functions here. When we get messier functions later, this won't be the case. How about the range? What kind of outputs can I get out of squaring a number? Why can't I get all real numbers by squaring?
Sometimes you might end up with imaginary numbers.
No. I didn't put imaginary numbers in, so I'm not going to get them out. I'm not talking about the square root function here. That's going to be a bigger problem. Let me think about this. What if I have a positive number and I multiply it by itself? What kind of number do I get out? Positive number, right? What if I have a negative number and multiply it by itself? I still get a positive number. You see that? I'm not going to get a negative out of it. It's just not possible. You guys see that? So if I feed in real numbers, I'm going to get positive real numbers out. Can I get 0? Yeah, if I put 0 in, I get 0 out, right? So this should tell me that my range should look like something from 0 to yeah, I mean 0 kind of up, right? 0 and up maybe would also be a and I need to make sure that I tell you to include 0, right? So included.
It has to be up infinity.
Okay, so now we need a way to write this, right? Because I've written 2 English statements and I'd like to have a math statement instead. So the math statement I would write would be 0, infinity, with brackets like this. Have you guys seen brackets like this in the book? Yeah? Okay, so this is an interval. So what this thing means is this means all the numbers, well, all the real numbers between 0 and infinity, including 0, that's what the square bracket means. So the square bracket says include this one.
Did you just write all whole numbers? Simple for whole numbers?
So I don't mean whole numbers here. I mean real numbers that are positive. I can certainly get the square root of 2 out of this thing by squaring the 4th root of 2. Does that make sense? Probably not. I know I can get pi out of this thing by squaring the square root of pi. Does that make sense? So there are lots of numbers I can feed into this and get kind of weird stuff out of it. This is a hard way to see this, right? This reasoning. A much easier way to see this is to graph and look. Okay? You guys want to see that approach? Okay. So domain and range by graph. And this is maybe what I would recommend as kind of the good approach for this. First time. So first step, graph your function. Okay, so what does x squared look like? It's a parabola. It's pointed up. And it goes through 0, 0. We're going to talk more about how to graph parabolas today. Okay.
Does it point up when it's positive?
It points up when the a that you would put in the quadratic formula is positive. Does that make sense? We're going to talk about that some more today too. So use techniques that we'll develop later to get a graph, or get a graph out of your calculator, or Wolfram Alpha or whatever. Somehow arrive at a graph, then what? See, the domain is the inputs, right? That should be along this axis. So I want to know which things on this axis have graph above them. So I don't need to worry about the vertex here. We're going to talk about vertices later, but for right now, all I want to know is where is their graph above the x-axis? So one way I could figure that out is I could think about just smashing this whole picture down and looking at where the graph ends up smeared. That kind of make sense? Put your hands like this, put them together, and then wonder where the graph went. See that? It's a line, right? But it was everywhere. When I smash, it was above all this stuff. You guys see that? So that's telling me that the domain is everything, because everything was covered when I smashed this way. If I want to find the range, I'll smash this way onto the output axis, right? When I smash this way, what do I get? Yeah, I see that it's just the positive things, and I see that it includes 0. You see that? So that's another way that we could do this. And we'd get domain is the real numbers again. And the range is just 0 to infinity. This bracket, by the way. Yeah, so what does the open bracket mean? So the open bracket, the square bracket means included. The open bracket means not included. So why isn't infinity included in this? Yeah, because it's infinity, it's not a real number, right? It doesn't have a spot on the number line. It's kind of a thought at the end, right? You guys okay with that? So we never put square bracket at infinity. We're just not going to play that game. There's a class to play that game, and this one isn't it.
Is it just for infinity?
So if we're doing...
Yeah, for infinity, it always gets a round bracket. Other numbers can get either round or squared, depending on whether they should be included or not.
So on our test, if we put a parentheses instead of square bracket, is it wrong?
Yeah.
Yeah?
Yeah. But you get partial credit, right?
Okay, so if we see a 0, put this, or whatever number it's starting with, is square.
Do you mean to include it or not?
Okay, so if it's included, do the square.
If it's not included, round.
Okay.
I don't really understand why we have 2 different names.
Why I have two different ones?
Like you have the square one and then you have the round one. Wouldn't it?
Alright, so on this one it's square because it includes 0. And it's round on this side because it doesn't include infinity. Because infinity is not a
But could you
real
put,
number.
like, the circular one on the other side?
Yeah, and then it would
Or
mean
complete-
not including 0 to infinity, which is also not included.
Oh, okay.
Does that make sense?
Yeah.
This is going to make maybe more sense when I'm doing something like, okay, let me try another example, okay? Let me say that we have some little whoopty like this. Here's a function graph, right? It passes the vertical line test, so it's a function. Okay, I want to know about the domain and range of this function. Does that make sense?
Is it going to be different because you want to build in one circle and the other?
Yeah, it's going to be a little bit funny. So maybe here's 1, 1, 2, 3, 4, 2, 3. Okay? So now I want to know about domains and ranges. So I should smash this way onto the input for the domain, right? So when I smash this way, where does that graph end up smeared?
On that right side on top.
Yeah, on the right side between
1 and 4.
between 1 and 4, right? You guys see that? When I smash this way, that stuff ends up smeared in here. So my domain is going to be something like 1 to 4, and now I need to decide on brackets. So do I put open or closed brackets on each thing?
Close bracket by the 1 and open bracket by the 4.
Exactly. How do you know that, CJ?
Because on the dots that you have, one is colored in, meaning included, and then the other one is open.
You guys see that? When I put 4 in, or 1 in, I know what to do with it, right? I go up, I find a dot. There is a dot, so I can follow it over and get the output. Okay, see that? So when I put 1 in as an input, I go, okay, what's the output? I go up to this thing. Then I go, okay, I can follow that over and get the output out of it. When I try to do the same thing with 4, I go, okay, I should go up until I find the dot. There isn't a dot above 4. You see that? There's that hole where there's nothing in it. That doesn't tell me what to do with it. Right? So there's no dot above 4. I don't know what to do with 4. That means 4 didn't fit into my function. So I don't include it. You see this? So if I was reading this thing in English, I would think numbers between 1 and 4, including 1, not including 4. Does that make sense? Okay, how about the other way? What's the range? Okay, so let's see. So for the range, we should smash onto the output axis, right? So we go this way. We get goop, right? Our graph smeared between 1 and 3. Okay, now which way are they included or not included? They would still be the same order, right? The 1 is included, the 3 isn't. You guys see that?
Why is that again? Why is that here?
Okay, because 1 is an output, right? There's a dot across from 1. There's no dot across from 3. You guys see that? I really do think about this thing as being ink, and I'm smashing. And then I'm wondering, where did the ink end up? Well, the ink went from 1, because there was ink here. And then there was ink all the way up, and then when I got to 3, there wasn't any ink. Does that help a little bit?
Yeah.
Don't get attached to the idea that they have to resemble one another.
why are we putting 4 on the domain instead of 3?
Because on the domain, right, when I smash this way, I actually do get to 4.
Oh, okay.
On the range, right,
Well, yeah, okay.
yep, we're smashing the other direction, so we don't include it. Is this getting somewhere? This is coincidental. Don't get attached to this. The brackets don't have to be the same. You have to check every time. They can be like this. They can be opposite. Mixed bag. Yeah. You guys want an example where they're reversed? Yeah. So let's make a very similar function, right? And I want them to be reversed. So I would like 1 to go someplace and 4 not to. So let me try this. First, is this the graph of a function?
Yes.
Because it passes the what? That's the vertical line test, right? Okay, so this is in fact the graph of a function. What's the domain of this function? So again, when I smash, right, I get 1 to 4, and then I have to decide on brackets. So does 4 go someplace?
No.
No, because it has an open dot above it, right? Does 1 go someplace?
Yes.
Yeah, 1 goes someplace. Okay, now when we talk about the range, see, so when I smash again, I get 1 to 3, right?
So.
And now I need to decide on brackets. Yeah, but now 3 has something that goes to it, but 1 doesn't. You guys see that? These can be a totally mixed bag like this. So things where they're like this, right, where one's closed and the other one's open, they can result in things where both are open or both are closed. It takes a little effort to make an example like that, but don't get attached to the brackets here meaning anything about the brackets there. So.
Look around to switch range.
Oh, it is.
Yeah, and then you took the different dots when you were trying to write the domain range. But you switch them when you were trying to add them down. Oh, okay, I'll count it out.
Yeah, please. I think you have a valid point, but I don't understand it.
Yeah.
You guys okay? Any questions about this? Do you guys want to see a function that we know about that's not a picture that doesn't have an R here?
Yes, please.
Okay. So we don't know a graph for this one, but I'm going to give you the graph for it just so you can kind of play along. So let's find the domain and range of f of x equals square root of x. Okay, so in this, we're playing real numbers. Okay, no complex numbers. Okay, no complex numbers. No, it's just poorly drawn. Okay, so let's see. Here's a graph. You get this out of your calculator or Wolfram Alpha, or I told it to you, or some other magic. There is a good way to get this. We'll get it later. We don't have this tool yet. We need a couple more chapters to get this tool. But for right now, let's just assume that this is a graph. Okay? So now let's play the same game we were just playing. What are the domain and range of the square root function? Yeah, you see that when I smash this way, there's no dots above any of the negative stuff, right? That's really because I don't know what to do with a negative when I feed it into the square root function without going to complex land. Right? And I don't know how to draw a complex land, so I'm going to leave that off, right?
Do we always have to smash the thing? We just-
Yep. It's okay, you're not hurting it.
Alright.
So if we crush this way, right? Now I've used an even more violent word. We smash it this way, right? We're going from 0 to infinity, right? And now we need brackets. So what brackets do we put on these?
Close bracket and then open bracket. And then the other one is open.
Okay, there's a closed bracket on the 0 because 0 has a dot above it, right? I know what to do with that. And we have an open bracket at infinity. Why? Because there's always an open bracket at infinity because infinity is not a real number, right?
So then when we have these problems, do we know that every time it's square root, it always starts at 0 and then arches away?
Yeah.
Okay.
Well, okay, so as long as it's the square root of x.
Okay.
If it's the square root of x plus 17, things are different.
But it will always arch in that one spot. So if we have to draw it, we always know to start at 0 and
Yeah.
arch.
Yeah, so if you guys want to draw square root of x, this is the picture. This is always the picture for that function. Does that help a little bit? I don't know. I'm hoping that doesn't come up often yet, but yeah, this is the picture for it. This is a good one to have in your head. Later, this will be kind of important that you have something like this in your head. What's the domain for this one?
You mean the range?
Sorry, we got the domain. What's the range? Yeah. Same thing. You guys see that?
No.
So smush this way, right?
Oh, so 0 is
So I still have 0 and it's still closed. And then this other thing I have to wonder, does this stop going up, right? You guys see that? It so happens with this function that it doesn't. It is possible for functions to stop going up. This one doesn't. If a function stops going up and someone's giving you an honest picture of it, it should look something like this. They should put some kind of a dotted line on there to indicate to you that it's no longer going up. This is a kind of a poor drawing. But we should be able to calculate domains and ranges for this one. Let me give you some values. So let's say that's pi over 2, and this is minus pi over 2. This is 0, 0. So what are the domain and range for this one?
So negative pi over 2, and then negative pi over 2 because we smashed them.
Okay, which thing are you answering?
A range.
Okay, so the range is the more interesting one here. That's when I smush this way, right? And I get, that's supposed to be a dash. That's positive pi over 2. So we're clear. So I have from minus pi over 2 to pi over 2, there's stuff, right? Okay, now I need brackets for that. So does anything get, do I actually get goop on those?
So they both get open parentheses?
Yeah, these are both open. You guys see that? Because this thing kind of tails off. It never really gets there, but it gets really close, right? This function's a little bit beyond the scope of the course, but you guys are playing along really well today, so I would like to kind of advertise cool things. What's the domain? So if I smush this way, what do I get?
It should be going both ways forever.
Yeah, going both ways forever. What do we call that? Okay, we could call that minus infinity to infinity. And what kind of brackets do those get? Open ones. Or, what's the other symbol for this thing?
What?
Yeah, for minus infinity to infinity, the other symbol we have is the funny R.
Oh.
For those of you who are interested, this is the function arctangent. This is a function that comes out of trigonometry class. This is a function called arctangent. I know you. So for those of you who would like to know, this function has a name. It's arctangent. You can find it under the tangent inverse button on your calculator. There's a button for this function on your calculator. It must be important somewhere if they put the button on the calculator, right?
That's in the next class.
Yes, that's in the next class. But we can still play domains and ranges with it, right? We don't need a formula for it. We just need a picture. We can get a picture out of our calculator because there's a button for it. Okay. This is good. I wanted to talk about domains and ranges anyway today. So, let's see. What else? We should talk about 8.3. Did that help a bit? They ask a lot of questions about domains and ranges, right? Yeah. There's one more thing we should add to intervals, which is how do you stick intervals together? You guys know what I mean? Okay, so going back, this is not 8.3. Sorry. If we had a function that looked something like this, pretty cool. Function, 2 pieces, whatever. If I think about, all right, maybe here's -1, -2, 1, 2, 1, 2. If I want to get the domain of this thing and the range of this thing, how do I do that? Yeah, we should smash the same way we were smashing before, right? So which one of these is easy and which one's weird? Yeah, domain's weird. Range is easy, right? When I smash sideways, what do I get?
So would that be like x is equal to or greater than -2, but less than 2? Is
Okay.
it where you draw like the greater
Okay,
than sign?
don't do that yet.
Okay.
We're still going to play intervals. That's another way to express intervals, which is fine. But we're going to play intervals right now. So I want to do the range first because it's the low-hanging fruit, right? It should be easy, I hope. So when I smash this way, what do I get? 1 to 2, and I have to decide on brackets, right? So what are my brackets?
Box.
Box and a parenthesis. Good.
I don't get how you got 1 to 2.
Smashing this way, right? Onto the outputs.
Oh, right.
So I'm getting stuff covering between here and here, right? And then this one has a dot, and this one doesn't. So I got closed, open. Okay?
It's like that, you have one open, that means forever, and the other one is that one. In other words, the little circles mean something.
Yeah, the little circle means I don't know what to do with the number underneath that. All right, how about the domain? when I do the domain, I smash, right, vertically, and I get like this stuff.
Did you have two of them? Like two?
Yeah, there's two of them, right? There's -2 to -1 and 1 to 2. And now I need to decide on brackets. So what are my brackets? Okay, so there's a closed one above -2 because there's a solid dot there. There's an open one above -1. How about 1? That one's open and 2 is closed. Okay, now this is the tricky part. We have to decide on a symbol to stick in here that means this stuff and that stuff.
The union one?
Yeah, so there's some options. You can write and if you want for now. This shorthand for this, the math symbol, is this kind of U-shaped thing.
I remember that.
This is like the math version of an ampersand. You guys know what an ampersand is? So when you see this thing, think
Union, unified, or whatever, right?
Oh, the and.
it's called an ampersand.
It's called the and.
It's called an and sign. Sure. Right? So you think this means and, right? I want this stuff and that stuff to be my domain. Big plus sign, sort of, right? You guys cool with that? This is the symbol with which I add intervals together. Right? This is a plus sign for intervals.
So the parabola will be the
Yeah, so it's a U.
okay.
It's a stylized capital U. Stands for and. Yeah, don't do the upside down one. We don't have a meaning for that right now. They're logic symbols. It is or, but I don't want to talk about what that means in interval land because it does something. You guys cool with this? Yes? Ish?
Yeah, you made it a lot clearer.
Okay.
So does it mean something different in algebra 1?
No, that'll mean the same thing all the way through to the end of grad
You
school.
like the and symbol?
No, I like that one. That U, that's the symbol you want. But you guys aren't, we haven't talked about set theory yet. We haven't talked about intervals really a lot. If you want to use an and, go for it. I would prefer if you used a symbol that meant something to you at this point. That U thing doesn't mean anything to you guys yet, so if you don't want to use that, just put an and in there, it's fine.
But it's the same thing as algebra 1, correct?
Yeah. All right, let's see. Other questions? Otherwise, I'm going to talk about 8.3. No? Okay. So 8.3 is about absolute value function. Okay. So the kind of fundamental example of this thing is the function that I would call the absolute value function. Okay? So the difference between an absolute value function and the absolute value function is going to be hard to see, maybe. If it doesn't look like this, but it has absolute values in it, it's probably an absolute value function. Okay? This is the kind of basic one, so this is the one we're going to play with first. You guys remember seeing this? We talked about this a long time ago. Yeah. So what does this thing do? Yeah, very nice. This is the thing that returns distance from 0, right? So this is
What is the value FCT function? So
function. Yep. And then this is the thing that returns distance from 0 to x, right? So if I go like this, here's 0. Here's a value, say 3. This distance, right, is what we mean by the absolute value of 3. What's the absolute value of 3? 3. Right? Okay, good. How about if I did -4? Yeah, it's 4 because this distance, right, is 4. You guys cool with that? Okay. This is the basic one. What does the graph of this thing look like? It looks like a V. Good. Where's the V centered? Or, yeah, 0, 0, and then it splits this way and this way. You guys cool with that? Okay. I want one more thing out of you guys for absolute values, which is this kind of strangeness. This is going to be our first exposure to what's called a piecewise function. Piecewise? I'm going to write that word down in a second. All it means, and it's really just a fancy word, where we're going to define the function with 2 rules. We're going to use a rule on one piece of the real line, and we're going to use a different rule on a different piece. Okay? So how does this thing work? What if the number is bigger than 0? In other words, if I put in an x that's positive, what do I get back? Yeah, I get back the same thing, right? You guys see this? So if I apply the function f of x, right, the absolute value function, to an x, I can check. If the x is positive, it just gives you back the same thing, right? What if the x is negative? It gives you the positive version of that number, right? And this is a little trippy, but that's minus x. Does that make sense? If x is negative, right, then this is a minus minus, gives me the positive version of x. You guys see that? You want to do some examples?
Yes.
Okay. This is not different, by the way. This is the same thing, it's just expressed in a different way. So I'm going to play with this version of it. This is called piecewise. Okay. And all piecewise means is that it's defined on pieces. So here's one of the pieces, here's the other piece. Cool. So calculate f of, say, -7. So is -7, if I want to jam that in here, is it positive or negative? Negative, right? So I should put a minus sign on it. So what's minus minus 7? Positive 7. Okay, see how that worked? That got a minus sign, right? That was my rule, right? F done to negative things puts a minus sign on them. Done to positive things, it does nothing. So let's try it with a positive thing. So what's f of pi? Pi, right? Because pi is bigger than 0, it goes in this piece. Right? So it comes out pi. Cool. Remember, pi is just a number. Specifically, it's like 3 or something, give or take. So what's f of minus pi? Okay. That goes in the negative part, right? So I get minus whatever I put in. So I put in minus pi. So my output is minus minus pi, which is plus pi. You guys see that this does the same thing you're used to doing? So this is just another way of expressing our rule that we had before. So earlier we had a rule way, which was to calculate the distance from 0. We had another rule, which was this thing. We had a graph, which was this thing. Now we have yet another way, which is this piecewise thing. This is super useful later on. Right now, I know it seems a little cumbersome. What's up?
What will be f of I?
That one's very confusing and a very good question. The answer is 1.
Why?
Oh, man.
Because that one is tough. So if you applied this function to I, you have to ask how far is I from 0, right? It turns out that there's a reasonable way, which requires a little calc 2, to draw the complex numbers this way.
Do we need that
No.
right now?
No, not at all.
No.
You can ignore this part. So the reason it's 1 is really that when you square I, you get something that has size 1. And then if you do it 4 times, you'll get 1. That's kind of a fundamentally weird thing, and it only happens when the size is 1. This is a very cool question, a little outside this, substantially outside the scope of the class. But. Okay, so all this is optional. Cool? Yeah. Okay. Anything else about absolute values? This is just the absolute value function, right? So if I want to draw a different absolute value function, for instance, let's say we were asked to, say, graph h of x is minus absolute value x. Okay. So how do I do this? Okay, let's start with a chart. That's a good idea. So I'm going to have x's and h of x's, right? Okay. What are your 5 favorite points? Okay. What do you get when you plug 0 in there? -0, which is 0. Okay. Okay, then 1 is your second favorite point. What do you get out of that? -1. You guys are getting good at function evaluation. This is very cool. 2. What do you get out of 2? -2. This is the part where we might have trouble.
Still negative.
Why is it still negative?
Because it's absolute.
The negative of the absolute.
Yeah, so I'm thinking here, right? Negative absolute value of -1, right? Then I have to do the stuff in the parentheses first, right? According to orders. And those little things, what do those count as? Those count as parentheses. So I have to do that first. So I get -1 means I get -1 out of this. Okay, how about if I plug in -2? I get -2 for the same reason, right? Because I do the absolute value first, I get 2, and then I toss a negative on. So, what do I think this thing looks like? Some axes, right? see. So it has the point on it. This guy, y. Zero is both an input and an output, right? And if a thing's on the graph, it's going to be a x comma, no, an x comma h of x pair, right? Right? To be on the graph, their points look like this. So 0, 0 is on here because 0 is the x and the h of x for that first set. What's up?
I thought whatever x was just equal to y. So if we put y, it has to be
I want you to put h of x.
oh.
The reason I want you to do that is I want to label this whole axis y. Right? I want to be able to talk about a point over here that's not necessarily on the graph as an x-y pair. I don't want you to get attached to the idea that y is h of x.
Oh.
Does that make sense?
Yeah.
All right. So we've got 0, 0. What's our next point on the graph? So over 1, down 1. Okay. Over 2, down 2. Left 1, down 1. And left 2, down 2. So what does this look like? Other than sloppy graphing, right? This should look like a V pointed upside down. I was going to have to move something to make that look right. You guys see this? So this thing looks like that one, but flipped over, right? So how about this? Is there a name for this thing? Okay, good, actually. Right, this is 0, 0. So we could call that the origin. That's true whenever we're drawing pictures, right? Whenever we have an XY axis set, that middle point is called 0, 0. In this case, it's called the vertex. Yeah, a vertex and a vortex are slightly different. Right, a vortex sucks up trailer houses or whatever, Oklahoma. And a vertex is the top or bottom of a graph. So, how about this guy? What's that one? That's also a vertex, right? The reason that we care about vertices, vertexes, I don't know what the heck the plural of this word is. The reason we care about these is that they're the tops and bottoms of things. That means they're the smallest this thing got or the biggest this thing got. We're often interested in that because we want to know when things like maximum profit happen or smallest expense. Does that make sense?
Yeah.
Okay, so that's what we're going to start with. So this is what I want you to have out of absolute value functions. I'd like you to be able to graph them. They get a little bit more complicated, but that's something for you guys to play with on your own, I think. Okay? Cool? Okay. You guys want 5 minutes? Okay, let's take 5 minutes. So, what? No.
No?
Yeah, sure. What's your question?
I was just going to ask what the favorite color was.
Pink. Neon, preferably.
Neon?
Yeah. I love all things neon. Okay. So let's see. We talked about 8.3 a bit. There's more of that in that video. So there's a couple more examples fully worked out in there. So if you want to play with examples, go check out that YouTube video. We did the easiest one. There's 2 harder ones in there, I think. So feel free. Let's see. Let's talk about 8.4 of it. We're going to blaze through things today because we set up a bunch of framework with this function talk we did over the beginning of the semester. So now we're going to learn some new functions. Okay. So we already learned lines, right? We learned absolute value. Now we're going to learn quadratics, which are just parabolas that we've already talked about, right? Okay, so there's not too much new stuff here. Okay, so a quadratic function looks like the kind of thing you jam into what? Yeah, into the quadratic formula, right? So a quadratic function is one of these guys. Maybe let's call this thing Q for quadratic. So a quadratic function of x is an ax squared plus bx plus c. Okay? No. So if I want to find the zeros of a quadratic function, I use the quadratic form. Does that make sense?
So we're not using the function, we're not using the formula, we're using the function.
Yeah, so this is a category of function, right? These are a kind of function. So they're sort of a rule, right? They go from numbers to other numbers. That's really what there is. Okay? So if we want to find zeros, so if we want to solve q of x equals 0, we use the quadratic formula. Okay? Yes? Good? Okay. Let's maybe draw some examples of graphs and then ask the kind of obvious question, maybe. Okay, so here's some examples of graphs. What's the basic thing like this? What's the maybe easiest thing you can get that looks like this? Okay, you guys probably aren't used to thinking in A, B, and C's, right? This is like super wildly confusing. Okay, so how about answer me this? Is f of x equals x squared, is that one of these? Yes, it is. How do you know it's one of these? So what are the A, B, and C for this one?
It's the A.
1, B is 0, C is 0. You guys see that? So this is a quadratic function, right? With A is 1, B is 0, C is 0. I should probably add this caveat before I screw things up. A can't be 0 for this. If A is 0, what is this thing?
A line.
Yeah, then it's a line. It's not a quadratic function. It's something simpler. You guys see that? So I'm going to need A to not be 0 for me to call this a quadratic function. If A is 0, it's a line. We already know how lines act. We had a whole section on lines. And we all fully understood it. I know that's a little bit ambitious, but I'm hoping you understood it at least a little bit and you recall some things about lines. These are a little different. What does the graph of this one look like?
Parabola.
Yeah, it's a parabola, right? This one opens upward. Why does it open upward? Because the A is positive. See that? Because the A is positive. There's a good reason for this. It's really that when I put in big numbers, right? When I think about what happens if I cram a really big number into something like this for the x, right? Well, I get A times a really big number times itself, which is a humongous number, plus B times the number, right? Which is no longer even big in comparison to this other thing. Plus c, which is probably like really small. Okay, see that? For instance, if I put in a million here, right? I get an a times a trillion plus b times a million. Trillions are way bigger than millions, right? So this is kind of the dominant term, which means that in the end, right, as I move way out right, that a, if it's positive, gives me a big number back. If it's negative, it gives me a big number that's negative. You guys see that? So if the a is positive, the thing points up. If a is negative, it points down. This is a really nice trick to know. Because why? What do I know about the vertex if it points up? Okay, first, where's the vertex on this one? Yeah, I said the origin, it's this point here. That's the vertex. And because it points up, this is a, you guys don't know this word yet, minimum.
What?
Minimum, it's the bottom, right? It's the smallest the function values ever get.
And that's only because it's pointing up.
Yeah, because it's pointing up, right?
Okay.
In this case, it's a minimum. If I had a different picture, like say g of x was minus x squared, this one looks like a parabola pointed downwards. How do I know it's pointed downwards? What's the a for this one? Negative 1, which is less than 0. Okay. What are the b and c?
Okay, what, can somebody tell me?
So I'm thinking a is negative 1. And then are there any x's here in my formula? There's squares, right? There's x squareds, but are there any plain x's? No, so b is 0. Are there any constants that I'm adding? No.
Hey, can somebody tell me why this A is 1 and B is 0 and C is 0?
Yeah,
There's
guys.
nothing there.
So the b and c are 0 because there's nothing there. The a is negative 1 because there's a negative x squared. Does that help? Okay. So now, where's the vertex on this one? Still at the origin, right? But what is it now?
Oh, because it's the highest.
Yeah, it's the highest point, so now it's a maximum.
Oh, okay.
You guys see that?
Yes.
Minimum's the lowest point, maximum's the highest point. Cool? Okay, so the entire discipline of calculus is developed basically to find these things. Minimums, maximums. Okay, but we have a way to do this for quadratic functions with what we know. Okay? My claim is we can already find these vertices. So let me throw another couple pictures up here. So keep in mind, they don't have to go through 0, 0. This could be one. Okay. What do I know about this one? Goes up. So what's the a? Yeah, a is positive. You guys see that? I don't need to know anything else about this. I know that if the a is positive, what do I know about the vertex? The vertex is a minimum.
It's still below the x-axis though, so would there be negative?
Yep. So there's the output, right, that's associated with that is a negative number,
Okay.
which means that maybe my minimum profit is a loss or something. That can happen. We have interpretations for negative numbers sometimes, right? So that's a minimum, and that's our vertex this time. We had another one. Sometimes they look like this. What do I know about the a here? A is negative because it points down. What do I know about the vertex? Yeah, the vertex is a maximum. What's the output associated with this vertex? Yeah, what do I know about the output associated to the vertex? Yeah, it's going to be a negative number. That might mean the best I can do with this situation is take a loss. Okay, see that?
And is that how you want them labeled as A is less than 0, A is greater than 0?
Yeah, I'd like you to be able to identify that. And then this is, yeah, this is just me giving you some examples of what things can look like.
So the output would be negative.
Yeah, so the output associated with this maximum value is negative.
Okay.
Cool? So let's figure out how to find the vertex. We can actually do this. We have a tool for this. I don't know why I'm capitalizing random words. How to find a vertex. And ID it as a max or min. One of these is easy, right? How do I ID it once I've found it? Yeah, I check whether A is positive or negative, right? If A is negative, that means the parabola opens down, so I get a max. If A is positive, I get a min. So this piece at least is easy, right? A bigger than 0 means minimum. A smaller than 0 means maximum. Okay, so that part should be easy. Okay, that's opening up or opening down. All right, so now how to find a vertex at all is a bit weird. Okay, so let me give you a statement first. The vertex is at x is negative b over 2a. I would claim you don't really have to memorize this. This comes from somewhere really reasonable. Where does this thing come from? From the quadratic formula. How do I see where this comes from the quadratic formula?
Shall I see it?
Okay, so, right? There's sort of a y here, right? Which is that the zeros, remember, if we want to solve for 0, we use the quadratic formula. So we know the zeros of q of x are at x is negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Let me rewrite that as negative b over 2a plus or minus this jump. You guys with me that this is the same formula? I just haven't combined using the common bottom that's here.
That's supposed to be a cube.
Yeah. I have crappy cubes. Sorry.
Is there a reason why you're not combining the two?
Yeah. So the reason I'm not combining them is that I'm thinking about symmetry here. So when I'm drawing these parabola pictures, they're not symmetrical by accident. They're symmetrical on purpose, and it's because there's an axis of symmetry in here. Okay? So this picture is symmetrical about this guy. And if those zeros happen, say here and here, these are negative b over 2a plus b squared minus 4ac square root over 2a, and negative b over 2a minus this business. Which is like, oh my god, what the heck is happening, right? But keep in mind, this thing's just a number, right? So one way I could think about this that would be maybe easier is to say, oh, well, I don't really care about what this thing is. This thing and this thing are the same, right? So let me just think about this as, this one happens at negative b over 2a minus a number, and this one happens at negative b over 2a plus a number, right? You see that? That really means, if I think about this distance, that's the number. Okay, see that? So what's the middle? Yeah, the middle's just negative b over 2a. There's nothing magic happening here, actually. You guys see that? It's just a thing about symmetry. It's saying, okay, if it's symmetrical, then those distances are equal. And if those distances are equal, and they look like this, then they must each be the number. So the middle has to be negative b over 2a. You see that? Kind of? Okay. So that's why this, right? It's the zeros are at these points, and the graph is symmetric. And I can't spell the word symmetric properly because no one can, so that stands for symmetric. There's too many M's in it or something. Cool? All right. You guys want to practice with one? Okay. So, find the vertex and ID it for g of x is 5x squared minus 4x plus 37. Give this a try, guys. Yeah.
Would it be easier if we just figure out the quadratic formula first?
No, definitely not.
Yes, I don't know. I'm just kind of confused.
So there's a tendency, right, to try to find the zeros of this first. This thing might not have zeros. They might be complex. This symmetry thing still works. It's kind of crazy, but it still works. So really, all I need to do is find A and B and calculate this. That's a lot easier than jamming on the whole quadratic formula.
Okay.
That makes sense? So what I want you guys to take from this lecture is this thing and this thing.
Okay.
Those are the crucial items here.
Which thing and which thing?
If you can take those two things out of this, this is what 8.4 wants. I would also like it if you knew that there was an up-down thingy for the A, right? That if A is positive, it goes up on the end, and if it's negative, it goes down. But that's about what I want you to take out of this. So can we calculate this? Where's the vertex? How about this? What are A, B, and C?
5, 5.
Okay, A is 5, B is negative 4, C is 37. You guys should hopefully be good at this from your practice with the quadratic formula, right? Here I'm not doing the quadratic formula though. This is easier. So vertex is at x equals what? Negative -4 divided by 2 times 5 equals 2 over 5. Okay? What's the point at the vertex? Right, that should be an ordered pair, right? Keep in mind this is ordered pair, not interval from earlier. Okay, what's the point at the vertex? What's the x value for the point at the vertex? 2/5. Okay, see that? Right? The vertex is at x equals 2/5, so x had better be 2/5 for the point of the vertex. Now, where's the y? Yeah, this should be on the graph, right? This should be an x comma function of x pair. So I should take 2/5 and plug it into my function. Right? So this should be g of 2/5, which is something that we could calculate, but a little bit messy, right? Yeah, here's my rule G. I'd shove 2/5 in there. That would get messy and occupy the time I want to use for a quiz. I would like you to actually do it out, but I'm not going to right now. You guys can calculate that, I hope. Cool?
Wait, what do you do?
Take 2/5, jam it in the function. Right, it should be on the graph, so it should be a x comma g of x pair. So this is a number, g of 2/5. I just take 2/5, I plug it in here, and I calculate.
That's when we set it to 0. And then
We're not setting anything equal to 0. We're just evaluating a function. Cool? All right. I was supposed to ID it. Is that a max or a min? Okay, so a is bigger than 0, right? Because it's 5. That means it points up. So it looks like this, which means the bottom of it is a minimum.
I'm sorry. How do you know that already? Because it's positive?
A is positive,
Okay.
right? Which means it looks like this. Which means that this is the bottom. If A was negative, it would look like this, and then it would be a top.
Okay.
But I know it's not that because it looks like this.
So we really don't want to plug into
Yeah, you definitely don't want to plug this into the
Yeah, 'cause
quadratic
that's
formula.
crazy.
This is a lot easier.
Okay.
Okay? This is a very cool thing. This makes my life way easy. There are a bunch of word problems about finding maximums and minimums. You just find the vertex. Done. Easy peasy. Sometimes you have to plug it back in if the value is what you want. Right? So if they ask for what's the maximum profit, then what they're looking for is an output of the function, right? We'll try some of those. Try some of those on your own, and when you get confused, we'll talk about them Friday. Okay? Let's see. I need to give you guys a quiz, so let's get a quiz. Your homework for 8.4 and 8.5 is already posted. I haven't talked about 8.5 yet. I may, if I have a chance, make a little video for you to get you started. Okay. Quiz. was find an equation.
Can you move a little